Okay, we're gonna check the problem of the rotating unbalanced mass. The example of this problem may be a kind of maybe washing machine or the engine of automobiles. And if we draw a schematic diagram, just a diagram to describe the system, we may have a mass, and inside a mass we have a small mass here. This is the mass of the machine, and this is a mass that rotates inside the machine. And yeah, with the rotation of this mass, maybe the radius of the rotation can be E. And with the position of the mass, the position of the mass is described by the angular displacement theta, and it travels about the fixed position O. This is just, how to say, a simple explanation of the system with unbalanced mass. In our actual system may be more complicated, but if we can assume it to be like this, we can tackle the problem by the same method that we're gonna learn from now. The machine may be put on a foundation that can be modeled as a spring and a damper. The machine itself has a mass, and the unbalanced mass also has the mass, and the mass is rotated about one fixed point inside the machine. And the generalized coordinate of this 1 degree of freedom system is the coordinate x, which is the vertical displacement of the machine. If we see the small mass m, the mass is connected to the machine by a rod. And by removing the rod, the effect of the rod, that can be a kind of 2/4 member or a string that try to pull the mass into the center of the motion to the point O, can be assumed as a force F. The mass M, if we put an axis, we have a direction on the radial direction and a direction in a tangential direction, or with the unit vector of the theta. And these two axes are orthogonal. If the mass M is travel with a constant frequency and constant magnitude of the velocity, they doesn't have the acceleration in the tangential direction, but they always have the acceleration to the center in the radial direction. And if we do the summation of force in the radial direction, it needs to equal to the mass multiplied by the acceleration in the radial direction. So the force, we assume it to be the minus F, because the radial direction is go to the outward direction. And yeah, the force is point to the center. So the sign will be the minus sign. How about the acceleration? Acceleration can be mv square dy by the radius, or it can be written in the term of the frequency or the angular velocity, m omega square, and multiplied by the radius. This radius, yeah, we can call it like eccentricity. Let me check. Yeah, eccentric. Yeah, the distance is the eccentric, and yeah, the force that the machine need to pull the particle to the center is equal to the mass multiplied by the acceleration. But for the machine also has a force, which is the reaction force, and go into the opposite direction with the same magnitude. And the angle or the position of the small mass is also related to the angle that the force act on the machine. And by removing the spring and the damper, and we assume the displacement is going into the upward direction, the force due to the spring and the damper also can written by the K and the Cx dot. And if we do the summation of the force in the x direction at the machine, it needs to equal to the mass multiplied by the acceleration in the x direction or the vertical direction. And upward is positive. And yeah, in the vertical direction, the component of the force will be F psi theta, and the force by the spring and the force by the damper is written by here by, yeah, and the mass of the machine, yeah, m x dot dot. And yeah, from the first equation and the second equation, from the first equation, the magnitude of the force is equal to m omega square and the eccentricity. And yes, and we can rearrange the equation of motion into the form by separate the motion and the input force. So we're gonna have mx dot dot plus cx dot plus kx equal to, yeah, we're gonna write the force in the term of the m omega square and psi of the theta. But yeah, the theta, we also know that it can be related to the angular velocity and time. So yeah, omega t. And we're gonna solve this problem by make it to be the complex number method. So the x is if this function, if the input is the psi function, x is the imaginary part of the c variable, and we're gonna replace the x variable in this function by the c variable, and from the psi function will be the complex exponential. So we're gonna have, yeah, and we're gonna divide the whole equation by the mass m to make it into the standard form. So we have c dot plus psi omega n c dot plus omega n square c equal to, yeah, mass of the unbalanced mass divided by the mass of the machine, and the radius of the rotation, and omega square, and replace the psi function by the complex exponential e power j omega t. And yeah, the c variable is the magnitude multiplied by the complex exponential. So the second derivative of this and the first derivative of this, yeah, we may familiar with. The second derivative, we have j omega square. And for the first derivative, we have just j omega. And we have omega n square. And the z is the magnitude multiplied by complex exponential. On the right-hand side, still be the same. And the unbalanced mass divided by the mass of the machine and the radius, and omega square multiplied by the complex exponential. So now the magnitude of the z can be obtained from the magnitude of the z can be obtained from this. So we may write it in the terms of the omega. It will be omega square divided by this, which is the natural frequency square. The natural frequency square subtract by this one, omega square. And the complex part can be 2 psi omega n j. And this is m multiplied by the radius and divided by m. And yeah, this is the constant, the complex constant here. We can relate the output x to the input here the omega by we can transform the C in the form of the frequency ratio if we divide this by the omega n square and divide this by omega n square. And we can turn it into the terms of the frequency ratio. So it's gonna be R squared divided by 1 minus R squared and plus 2 psi Rj. And M radius divided by the machine mass. This is the constant, the complex constant. And yeah, once the input is in the psi terms, and we assume the CT here and XT here. So yeah, the X or the displacement of the machine is equal to the imaginary part of the variable Z, but Z is the constant multiplied by the complex exponential. So R squared divided by 1 subtract by R squared plus 2 psi Rj. And I'm sorry. And multiply by mass, radius, divided by the machine mass, and the complex exponential. And yeah, or we can write it by a magnitude of the frequency response function and multiply by the M radius divided by M and psi function of the omega t plus a phase angle. So with this, the frequency response function H omega is this function. This is the frequency response function. So if we want to find the magnitude of the frequency response function, the frequency response function is R squared divided by 1 subtract by the frequency response function is and plus 2 psi Rj. This is the frequency response function. In order to find the magnitude, we may need to multiply it by a complex conjugate. And we did it before with the different function. We use the same technique. So yeah, the complex conjugate on the numerator and the denominator by the complex conjugate. And yes, we need to solve this. Yeah, the numerator, nothing changed. but the denominator, these are the complex conjugate. So what we have is 1 subtract by r square need to be square, and the second term also the j square will be -1. So we're gonna have 2 psi r square, and the numerator still be the same. And yeah, to find the magnitude of the frequency response function, it need to be the real part square plus the imaginary part square and take the square root. So the constant still keep the same one, the constant. The constant here still be the same, but to take the magnitude, we should deal with the real part and the imaginary part here. And the real part square is 1 subtract by r square and square. And the imaginary part square is -2 psi r square. And you get some hint from here. It seems like this term and this term are the same, and this term and this term are the same. So finally, the magnitude of the frequency response function, the magnitude of the frequency response function is equal to r square and divide by square root of 1 subtract by r square plus 2 psi r square. Yes, and yeah, this is the magnitude function r square divided by the square root of the first term plus the second term square. And I still do the same concept. I vary the theta or the damping ratio from 0.1 to 0.5 to 1 square root 2 and equal to 1. And I plot just only the magnitude. And I vary the frequency ratio from 0 to 10. And we see the magnitude plot of the frequency response function here. And yeah, what we see is that the damping ratio has no effect at very low and very high frequency. And the magnitude is equal to 1. Oh, this is a mistake. I need to say the magnitude is equal to 0 at very low frequency. And the magnitude is equal to 1 at very high frequency. So what is the physical meaning? The physical meaning is if the unbalanced mass rotates at very low speed, the vibration or the X displacement of the machine, almost be 0 displacement if the mass m rotate at a small omega. Does that make sense? If it rotates at very small speed, it not affect the vibration, not create the vibration. on the machine. Yeah, but if it rotates at high frequency, if it rotates at high frequency, the frequency response function has the magnitude of 1, which means that if it rotates at high speed and this is equal to 1, it means that the magnitude of the vibration will equal to this term, the mass, unbalanced mass multiplied by the radius of the rotation and divided by the mass of the machine. Is here. And at the natural frequency, at the natural frequency, if the damping ratio is 0, at the natural frequency, omega divided by omega n equal to 1, the undamped system, the magnitude will go to infinite. You may try to check it by yourself by reducing the damping ratio to be like very small, or may try it to be 0. You can see the magnitude turn to be the infinite. And what we can see more is with the more the bigger damping ratio, we can see the small magnitude. And yeah, with the same concept, sometimes we can see the peak magnitude. And the peak magnitude is related to the damping ratio. So to find the peak magnitude, the same concept is we need to find where the slope of the magnitude is equal to 0. And the function here, the function of the magnitude is r squared divided by, r squared divided by the square root of 1 subtract by r squared plus 2 psi r squared. Okay, to find the derivative d by dr of the magnitude, you have the, how to say, I hope you still remember the d by dr of a divided by b should be b dA by dr subtract by a dB by dr and divide by b squared is the differentiation of the fraction. So yeah, now we have the fraction here. If we want to find the derivative by r, we should use this formulation. And yeah, I may begin the first line and you may do the self-check. Our denominator is the square root 1 r squared plus 2 psi r squared, and we need to d r squared by dr, so we got 2r. And the second term, we have r squared, and we need to do the differentiation of this square root So what we have is we have 1/2 because the power of the square root is power 1/2. And yeah, inside the square root, we have inside the square root, what? Inside the square root, we have 1 subtract by r square plus 2 psi r square. And the power will be subtract by 1. So the power will be minus 1/2 instead. And we still need to do the differentiation of the term inside the parenthesis. So yeah, this will be 2 of 1 r square power 1 and minus 2r. And for the second term here, it will be 2 of 2 psi r, and d2 psi r by dr will be 2 psi. Yeah, and finally, this thing should equal to 0. And yeah, we need to try to solve the equation and make the equation equal to 0. And finally, yeah, today we don't have much time, but we can find that the ratio that we can find the peak of the magnitude will equal to 1 divided by 1 subtract 2 of the damping ratio square. And we can find the peak just only if when the 1 subtract by 2 psi square is more than 1. So the damping ratio will be between 0 and 1 per square root 2. Yes, it's the same concept with the previous one. We can find the peak at r equal to this, and only when the damping ratio is less than 1 per square root 2, we can find the peak. When the damping ratio is higher, we cannot find the peak anymore. Okay. And for the design example, this is just a brief concept. And yeah, the assignment, the third assignment, maybe the one problem in the assignment will be similar to this. And yeah, the idea is we may give a system that have a mass of the machine, a mass of unbalanced mass, and we can say that we can know that the machine may operate at one constant omega, or the range of the RPM of the omega, and the eccentric, the distance, the radius of the unbalanced mass may be given in the unit of the meter, centimeter, something like that. And the design problem is we may need to design a stiffness of the spring and the damping coefficient so that our system has the magnitude of the vibration less than maybe 10% of the eccentric. Yeah, in our system, we have the mass of the machine, and we have a mass, unbalanced mass, and we have the radius of the unbalanced rotation. And yeah, the radius of the unbalanced rotation may be like 0.1 meter, something like that, for example. And we want to design the K and the C so that our vibration, our displacement of the machine, the magnitude of the vibration is less than 0.1 of the radius of the unbalanced mass. And the idea to tackle with this problem is, yeah, we have the equation of motion. We have the equation of motion. And we need to derive the frequency response function. We may use the complex variable, like we may use the complex variable. And if we use a complex variable, it should be the complex exponential instead of the psi function. And yeah, the complex variable is a constant multiplied by a complex exponential. And to do the second derivative, we're gonna have the minus m omega square plus c omega j and plus k of the c e power j omega t. And on the right hand side, it still be the same, m omega square and the radius and the e power j omega t. And we can solve for the constant, the complex constant, by m omega square e divided by the m omega square k subtract by m omega square and plus c omega j. Yes, and we know that the xt is equal to the imaginary part, because it is a psi function. Xt will be the imaginary part of the c t, or it can be the magnitude. The magnitude of the m omega square E divided by K subtract by M omega square plus C omega J. And multiply by the sine function of omega t plus the phase angle. Yeah, and we want to know that the xt divided by the eccentric should always less than the 0.1 or 10%. And we need to decide the C and the K for the system so that, yeah, X divided by E is less than 0.1. We may assume K first. Yeah, we may know the machine mass, and we're gonna know the RPM that need to transform to be the radian per sec. And yeah, by this we may know the natural frequency omega n. And after we know the natural frequency, we may try to decide K so that our operating condition is not operate at the natural frequency. And after we get K, we may try to obtain the C so that it matched with this condition. You can see that we have a lot of solution, a lot of set of solution, a lot of possible set of solution K and C that can satisfy the requirement. Yes, so yeah, I think this kind of problem is interesting, and in order that you can review more the concept and try to practice designing the parameter by yourself, I may put this in the assignment maybe. And the second type of the problem, we know the unbalanced mass, and the last type of the problem for today is the base excitation. Base excitation means you're gonna have your car and you have the suspension. And the suspension have the K and C, and the wheel of the car is driven on the road contour. And yeah, the base is excited by a displacement YT. And we want to obtain the displacement of our mass xt as a function of the input yt. Yt is the input, and xt is our response on the system. So we begin with the free body diagram. We have a mass here, and with a positive x, we may need to assume that the excitation always have bigger magnitude than the displacement, and bigger velocity than the displacement, which means y always go bigger than x. And the force by the spring and the force by the damper can be assumed to be in this direction if y bigger than x and y dot is bigger than x dot. And yeah, the equilibrium of force. Okay, from here, so that we have the enough space. The equilibrium of force, summation Fx equal to MAX. And yeah, the summation of force, we have only the spring force K, Y subtract by X, and the damper force C, Y dot subtract by X dot should be equal to the mass multiplied by the acceleration or the vertical displacement. And by rearrange the equation, what we have for the system displacement, mx dot dot plus cx dot plus kx, and for the input, the thing that relate to the input is cy dot plus ky. So yes, the y, in this case, we may assume the y or the road excitation as a cosine function. With one frequency. So in this case, if we assume the road excitation like here, the base excitation like here, y may be equal to a magnitude of y multiplied by the cosine function. Yeah, in this case, if we want to use the complex variable c, if we want to use the complex variable, x should be the real part of the complex variable because we are playing with the cosine function. So we turn this into the complex variable c, and we're gonna divide m throughout the equation. So what we have is we have c dot dot plus the standard form c plus omega n square c. On the right hand side, yeah, the complex variable for the input y also be the complex exponential, and yeah, it should be we divide by m throughout the equation, and the first derivative still keep the first derivative of the y, and the zero derivative also still be the zero derivative of the road contour y. And yes, we know that the complex parameter is one magnitude multiplied by the complex exponential with the same frequency with the excitation, we assume. So by this equation of motion, if we do the second derivative of the z, yeah, we're gonna have the j omega and it's gonna be j omega square plus 2 psi omega n, and the first derivative is just j omega. And the zero derivative, we have omega n squared. And the z is the magnitude multiplied by the complex exponential. And for the right-hand side, here, we have c divided by m. And the first derivative of e power j omega is also j omega. And the second term, we do nothing with it. And it's gonna be y of the exponential. And we can relate, now we can relate the magnitude of the output to the magnitude of the input. We can relate this by this is like omega n square, and we can also turn this into the form of the damping ratio. So you may verify this, but we can transform this into the omega n square plus we know that the damping ratio is c divided by 2 square root km. And we can, this term, by this relationship, we can write it into the form of the omega and omega n. And also, this is this term, and when we divide by this term, we're gonna have the omega n square subtract by omega square and plus 2 psi omega and omega n j. We can relate the output and the input excitation, the magnitude of the output and the input. And also, if we divide the omega n on the numerator and denominator, we can also write this in the terms of the ratio r. It's gonna be 1 plus 2 psi rj divided by 1 subtract by r square and plus 2 psi rj. We can relate the output to the input by the frequency response function here. And if we want to obtain the x, which is the real output, x is the real part of the complex variable z. So x can be a kind of the magnitude of the frequency response function multiplied by the magnitude of the input and cosine of the omega t and plus the phase angle. Yeah, the magnitude of the z divided by the y is equal to the magnitude of this. And the magnitude of the z divided by y, we call it as a displacement transmissibility. Which means that the input has a magnitude of the displacement, and the output also has the magnitude of the displacement, and the displacement transmissibility, or the magnitude of the frequency response function, can tell us how the input magnitude affect the output magnitude depending on the frequency of the excitation. Okay, we will remember this. We will remember this form, and we need to try to find the magnitude of this. But lucky in this case, we have the complex number in the denominator and the numerator. We have the magnitude of the z divided by y. Z divided by y equal to the magnitude of 1 plus 2 psi rj, 2 psi rj divided by 1 subtract by r square plus 2 psi rj. We have the magnitude like this. And yeah, by the property of the magnitude of the complex number, we can just find the magnitude of the numerator divided by the magnitude of the denominator. So it can be the square root of the real part plus the square root of the imaginary part. And this also will be the square root of the real part square plus the imaginary part square. Yeah, you can take the square root of this. And yeah, once we plot this, this is the same function. Once we plot this, we found that yeah, it depends on the damping ratio. But if we go faster, if we drive the car faster, which means the omega is high, it seems like the displacement is less than 1. Here, small displacement, which means that although the magnitude of the excitation are the same, but if we drive the car faster, sometimes we cannot feel the vibration on the displacement of the car, which can be a kind of benefit if we think in the term of the comfort. But Yeah, we need to trade off with one drawback. If we see the force transmit, the idea of the force transmit is we have the mass of the car and we have the base excitation here. And yeah, the force that transmit by the spring and the damper will be K, Y subtract by X and C. Y dot subtract by X dot. And the displacement of the car is xt. And yeah, we still assume y more than x and y dot more than x dot. So the force that transmits to the car and the force that transmits to the road inside the suspension. Yeah, the force that transmits to the suspension from the car is equal to the minus, because it goes downward, minus of the spring force and minus of the damper force. And yeah, it's how to say, before this, if we do the summation of the force to the upper body of the car, we have oh, sorry. Wait a second, I have a few problems. Okay, I hope you still can see the screen. Yeah, if we consider the upper part of the mass, we have the K y subtract by x plus C y dot subtract by x dot equal to mx dot dot. But for the lower part that the force transmit, everything will multiply by the minus sign. But the important thing, we just consider the magnitude. Yeah, the sign is not that important, but the force transmit here means the force that transmit back to the transmission in the downward direction. But we know that the x can be written in the term of the magnitude of y and the magnitude of the frequency response function and the cosine of the frequency and plus the phase shift. If we do the second derivative of this, of the x, if we do the second derivative, we just have the omega come out from the cosine function and have one negative sign. If we do the second derivative, we're gonna have the minus omega square y and the magnitude of the frequency response function and the cosine function and the phase angle still be the same. And yes, the transmit force is equal to minus mx dot dot. So it's equal to m omega square and magnitude of y and magnitude of the frequency response function and cosine omega t plus the phase shift And before this, we have the displacement transmissibility, the magnitude of the output displacement divided by the input displacement. But for the force transmissibility is the magnitude of the force divided by the magnitude of the input by the input. So yeah, what we have here, input is this one. Yeah. So what we have here is we have the m omega square and the magnitude of the frequency response function. And yes, these terms we call the force transmissibility, FTM. FT is transmit force. Yeah, FT is transmit force, which is the force, but FTM is the ratio between the transmit force and the input. Is the force transmissibility. And yeah, by this, if we write in the terms of the ratio, the magnitude of the H omega, or the frequency response function, is this one. But yeah, by this, if we write this in the terms of the ratio, we're gonna get the R square multiplied by the square root. If you have time, you may try to derive this to obtain this. I mean, we may just maybe have the omega n into the terms, but the magnitude of the H omega is this one. Yeah, and this one is related to the R. And yeah, one thing that I forgot to mention is, I'm sorry, this one need to be the force transmissibility. If we want to make it to be dimensionless, we should divide it by a spring constant. Okay, and this is equal to this, and FTM here need to be this one divided by the spring constant. Yeah, you need to divide this by a spring constant, and you can arrange this into this form. By the way, a spring constant just only one constant variable, but if you plot this or you plot this, you still can see the trend of the force transmissibility. But what we can see in here is that if the damping ratio is more, we have the peak here, and sometimes we still have peak here. But the important thing in this slide is if you drive the car fast with the higher frequency, the force that transmit in the transmission is high, very high. So although in this page, if you drive fast, you can get the comfortness because the displacement transmissibility is more. But here, if you drive fast, the force transmissibility is high, and it can create some damage in your suspension system. Yes, I teach over the time, but that's all for today. Yeah, the content is a kind of maybe deep in detail and maybe more difficult, too difficult for you to understand in one time. But if you have time, like spend maybe one more round or two more rounds to check the record class and try to write it on the paper and derive the equation, I think you can get the concept. And the MATLAB tool to plot the things is not that difficult. I mean, the theory, you can review it later. If you still work in this area, you can open the textbook and check in the textbook for the theory. But the MATLAB code that you can obtain the plot easily, I think it's useful for you to work in this field in the future, and hope you enjoy. And that's all for me today. If you have any question, yeah, welcome. If you don't have any question, I'm gonna end the class by now. But please remember, next week and the next 2 weeks, you're gonna have the midterm exam. So we don't have class on October 5th and October 12th, but I will try to put an assignment on Friday night of October. And the due date, maybe one assignment, maybe 16, another one, maybe 23rd, you still have time to do it. And the assignment will be about this chapter, the force, the displacement, transmissibility, and frequency response function. And another one will be the free vibration, that you need to plot the response for a given initial condition. Okay, that's all. Have a good luck for the exam. ขอบคุณครับ